Okay.
Great.
All right.
Okay, great. So hello, everyone. So welcome again to our weekly seminar. We actually start for 2 weeks for the Chinese or Lunar New Year. Last week we had a great talk from Max Welling, and this time we have our wonderful Sergey Levin from UC Berkeley to give us the talk. So this is the talk a lot of you have been waiting for. So we're very excited, like every one of you. So a little introduction for Sergey. So Sergey finished PhD 2014 and joined UC Berkeley 2016. So thanks Pedro to let us know that. But Sergey actually spent some time between 2014 and 2016 at University of Washington. I myself actually was a graduate student at University of Washington in early 2000 for 2 years, not 2 quarters. So I know University of Washington very well. And so since Sergey, I would like to use this opportunity. So Sergey graduated PhD in 2014, and I also did an undergraduate and master's, and I finished them in 2009, all from Stanford. So I'm shamelessly very proud to say that I and Sergey overlapped for 2 years at Stanford. So Sergey is a very well-known researcher, even though he's extremely young. He's a very well-known researcher in machine learning in general, and in particular deep reinforcement learning. So you can see his names all over the conferences and in ICR, NeurIPS, XML, and many robotics conferences as well. So without taking too much time from Sergey, I'd like to let Sergey start the talk. Thank you, Sergey, for welcome to Baidu.
Great, thank you for the introduction. All right, so I'll start with some fairly high-level points about machine learning, and then zoom into the main topic of today's discussion. So, and by the way, as I said earlier, if any of you have questions you want to ask, please, by all means, feel free to ask questions. We should have plenty of time for that. You can ask them in the chat. You could also, during any appropriate pause, unmute and ask your question. That's totally fine too. So definitely don't be shy about that. So I'll start with a fairly big question. Why does machine learning work? And I'll start with a simplistic answer, and then I'll make it a little more complicated. So the simplistic answer is that modern machine learning methods, insofar as they generalize very effectively, they use lots of components, but the two big ones are the ability to leverage large and highly diverse data sets that provide very good coverage of the domain, and the ability to train very large and high capacity models. So these two ingredients are basically at the heart of state-of-the-art methods in image recognition, natural language processing, speech recognition. All these things are the kinds of effective models that actually get deployed in practice in industry. They use lots of clever designs, clever tricks, but at the heart of it, there's always going to be a large data set and a large high capacity model. And this has been the pattern again and again across different fields. But maybe we can step back a little bit and kind of ask, what is all this for? Why do we need machine learning? And maybe to give us some ideas about how to answer this question, we can ask an even more basic question. Why do we need brains anyway? And we're going to look for an answer from somebody who knows quite a lot about brains. Daniel Walpert is a neuroscientist who works on neuroscience of motor control. And he has this to say on the topic. We have a brain for one reason and one reason only, and that's to produce adaptable and complex movements. Movement is the only way we have of affecting the world around us. I believe that to understand movement is to understand the whole brain. Okay, so you might object that maybe this is a little reductionist, but there's a point here that basically the ability to process information is only useful insofar as it affects what you do with it. And for a person, that's how you move your body. So I would put forward kind of a postulate that basically borrows this idea and say that, well, we need machine learning for one reason and one reason only, and that's to produce adaptable and complex decisions. Machine learning systems aren't necessarily hooked up to a body, but insofar as they're doing something useful, they are making decisions. And sometimes those decisions are, it's very clear what they are. So if you are actually controlling a robot, maybe your decision is how do you move your joints. If you're controlling a car, it's how do you steer your car. But if you have an image classifier, well, it's also making decisions. You could say, well, what is that decision? Maybe the decision is the label that it outputs, but not necessarily. So if you have a computer vision system and it's outputting a label, you do something with that label. It actually affects something in the world. Otherwise, what's the point of having it? So maybe you're going to tag people in a photograph, and you're going to present that to some user, and your goal in doing that is to increase user engagement, or maybe increase your ad revenue or something like that. So if you ask what happens with the label afterwards, then it becomes a little clearer how this is really a decision that has repercussions on the world. It has long-term consequences, and it's a decision that should be made with the aim of, optimizing for some end result. So these are all decisions, and they lead to consequences. So machine learning, in some sense, is automated decision-making, whether we like it or not. And typically, supervised learning problems, like the ones that I mentioned in the very beginning, image classification, speech recognition, NLP, we typically frame them as supervised learning problems because supervised learning allows us to put forward assumptions that make these problems easy in some sense. For example, we might assume that the data points are independent. We might assume that outputs don't influence future inputs. We might assume that ground truth labels are provided at training time. These are simplifying assumptions that make it a lot more manageable to use large data sets and large models, which is very important. Other domains like autonomous driving, robotics, automating inventory management, automating stock trading, these are also overtly decision-making problems that often don't satisfy these assumptions. Where current actions influence future observations, the goal is to maximize some utility rather than to match a ground truth. Optimal actions are not provided, and so forth. So it might seem like these are different things. But all these challenges are not just issues for control. In many cases, real-world deployment of ML systems, the ones that make those assumptions at the top, the easy assumptions, have the same feedback issues. And those simplifying assumptions are actually, they're a little bit of a delusion. For example, imagine that you build a system to predict traffic, and you're going to deploy that on an app that users will use to navigate to different places, and they're going to go to the places that have less traffic according to your app. Well, now your app is going to change the traffic patterns if it's deployed at a large enough scale. So even though it seems like you're solving a prediction problem, what you're really doing is you're controlling the flow of traffic through your app, maybe very indirectly, maybe very stochastically, but the feedback effects here really matter, and it is not IID, and your actions do influence future observations, and if you're using a supervised learning method, you're ignoring this. So if ultimately machine learning is always about making a decision, why don't we treat every machine learning problem like a reinforcement learning problem, right? Reinforcement learning is the branch of machine learning that deals with decision making, so why aren't we all doing this? Well, there's a reason for that. We all have reasons for doing what we do, and it's because reinforcement learning is really two different things, and that's basically the problem. First, it's a framework for learning-based decision-making. So reinforcement learning basically takes us out of the standard supervised paradigm where you have IID inputs and your goal is to predict ground truth outputs, and into a sequential decision-making paradigm where you look at a state, you output an action with the aim of maximizing utility and with full recognition of the fact that this action will affect your future state. So that's good. That's what we would like to do this because this is a better model of how the world works. But reinforcement learning is also another thing. It is a framework for active online learning for control. If there's a question? Okay. So it's also a framework for active online learning for control. And if we open up, the Sutton and Bardo textbook on reinforcement learning, you'll see this classic diagram. It's about an agent that iteratively interacts with its environment, collects some rewards, modifies its policy or value function, and keeps repeating this process. So fundamentally, in its most basic form, it's an online learning process. So to kind of summarize this in a cartoon, your agent interacts with the world, uses that interaction to modify its behavior, throws out the data collected, goes and collects some more data, modifies it again, and this is done a very large number of times. So the thing on the left, this framework for learning-based decision-making, that's very good because almost all real-world learning problems look like this. The thing on the right, this active online thing, it's pretty neat because that's, we might imagine that's how humans and animals learn, but almost all real world learning problems make it very difficult to do this. It's very difficult to set up an active online exploration procedure, for example, if you're prescribing treatment plans to patients. You don't want to do online exploration starting from scratch with an autonomous car because you're going to kill someone. So many real world problems make it very difficult to instantiate an active online learning framework. but they demand a framework for learning-based decision-making. So that's the conundrum we're in. These two things, we want one of them, but we kind of would rather pass on the other one in many cases. Not in all cases, but in many cases. Now, at this point, some of you might object that, well, okay, but this like works in practice, right? So this whole online thing, maybe we shouldn't make too big a deal out of it, because there have been some really impressive results playing video games, beating the world champion at Go. Like this is like serious stuff. But what I would say here is it's very instructive to compare side by side the kinds of domains where classic deep reinforcement learning has been successful and the kinds of domains where supervised learning has been successful. The domains on the left, playing video games, some of my work on robotic control in laboratory settings, and of course, the AlphaGo result, these are all characterized by fairly complex tasks, but in fairly narrow closed world environments. So Go is not easy, but the rules of it are known, and the boundaries of the world of Go are very well understood. The AlphaGo bot doesn't have to worry about the opponent spilling coffee on the board. Like that's just outside of the rules of that universe. The universe is well contained. For the supervised learning stuff on the right, these are open world problems. Recognizing images is valuable insofar as you can recognize any image that someone takes a photograph of. Recognizing speech is valuable insofar as you can do it in open world settings, not in closed laboratory settings. So there's an enormous gulf between the settings where RL has been successful and where supervised learning has been successful. And it's the gulf of variability, of generalization, of open world generalization. And if we want to take an online reinforcement learning paradigm and apply it to these open world settings, then we need the large data sets. And every iteration, we collect an ImageNet sized data set, use it to update our policy, and then throw it out and repeat this again. And that's, of course, never going to scale. So can we make RL look more like supervised learning? So basically, can we go from that thing on the left to the thing on the right and discard the active stuff? Well, so on policy RL, that's kind of the classic paradigm. That's where you interact with the world, update, you throw out that data, and then you interact some more. And what we'd like to do is develop methods for offline reinforcement learning, where the data has been collected, just like in the supervised learning setting, by somebody else. Someone collected lots of data, and it's just sitting in a data set somewhere. It's sitting on a server. It's sitting on your hard drive. And you'd like to load up that data and use it to allow your algorithm to basically understand how the world works and distill out of that data set the best possible policy you can get. And then once you've got that policy, then you can take it and use it to actually do stuff. Of course, in reality, you might deploy that policy and collect a little bit more data afterwards, but that's kind of the easy part. The tough part is how do you use that big data set to distill out a policy? And that's what I'm going to focus on in today's talk. So the kind of workflow that we would like to get with an offline RL algorithm is one where you first collect a data set using any policy or mixture of policies, and maybe someone else actually collects the data set for you. And it might include humans performing the task. It might include some existing system performing the task, random behaviors, or any combination of the above. And this is typically done only once. Now, you might go and collect even more data, but you would just append it. So you wouldn't throw it out. You would always just keep accumulating. And then step two is run offline RL on this data set to learn a policy. You can think of it as the best policy you can squeeze out of the provided data. So distill that data down to the best behavior that the data supports. And then deploy the policy in the real world. And if you're not happy about it, tweak some hyperparameters and go back to step two. But reuse the same data. There's no need to recollect the data. Just like when you want to tweak your computer vision model, you don't go and recollect ImageNet, you just tweak the model. And if we can develop effective algorithms for this, then we can apply RL to lots of settings where it has been difficult to apply the classic online active learning paradigm. Things like inventory management. You don't want to do random exploration for how to manage warehouses for a giant multinational corporation. That's very expensive. But they probably have lots of logs of how those warehouses were managed in the past, and that can form a really nice data set. Prescribing patterns of treatment to patients. Definitely don't want to experiment with that. But again, there's lots of historical data if you can get your hands on it. And maybe you can synthesize better treatment plans than the best doctor. Maybe you can analyze what millions of doctors have done and distill out the very best possible behavior from that. Scheduling plans of scientific experiments, controlling power plants, and of course, controlling robotic systems. So I'm going to talk about why offline reinforcement learning is difficult in a mathematical sense. How do we design offline RL algorithms, basically the basic building blocks of modern offline RL? How do we evaluate offline RL methods? And then how do we apply them to various problems? And here I'll talk about some of the robotics problems that I'm particularly enthusiastic about. But remember that all of this stuff is not necessarily about robotics. It's really about this range of problems where we'd like to apply RL, but where we don't want to do online active exploration. All right, so let's start with some of the bad news. Why is offline RL hard? Before I dive into this, I want to give you all a very quick primer on the basics of off-policy reinforcement learning. Many of you might be already familiar with this, but this is just to get us on the same page in terms of notation. So in reinforcement learning, you have an agent, and that agent interacts with the world by taking actions. We call them A. And the world responds with states S and a reward signal R of S comma A. And the goal of a reinforcement learning algorithm is to acquire a policy, pi of A given S, such that this policy maximizes the long-term expected sum of rewards. So you want to maximize reward over all time. It can be discounted, it can be undiscounted. Typically it's discounted, but I left that out for simplicity. And a very useful object for doing this is something called the Q function. Q of st comma at gives you the expected reward that you will get if you take action at in state st and then follow the policy pi thereafter. And this is very useful because if you can find the Q function for a policy pi, you can recover a new policy that is at least as good or better by basically taking the action that is the argmax of Q with probability 1. So this is the basis of policy iteration, essentially. You can also skip the middleman and you can implement QLearning. QLearning basically puts the max right into the Q function update, and it aims to enforce this equation. This is called the Bellman equation. So it basically aims to find a Q function that for every state and action is equal to the reward plus the max of the Q at the next time step. And if you can find a Q function that satisfies this, then the corresponding greedy policy will be the optimal policy. So if you enforce this equation at all states, then you're in business. And typically the way we do this is by minimizing the difference between the left-hand side and right-hand side. And we do this using data. So we can't enumerate all possible states and actions, so we use sampled states and actions. And the wonderful thing about QLearning is that these states and actions don't have to come from your latest policy. They can in principle come from any policy, in principle. And then you just solve this regression problem and you get hopefully a good Q function. Okay, so that's basically the idea. And this talk is going to focus entirely on dynamic programming methods, basically QLearning methods. But there are other methods too, based on things like importance sampling. I just don't have time to cover them, but keep in mind, this is just one of the possible recipes. All right, so here is a brief summary of how we use this basic formula to create an off-policy algorithm. So the key idea is that we don't need on-policy data to enforce this Bellman equation. So what we're going to do is we're going to collect a data set using some policy, and we're going to add it to a buffer, B. And then in an inner loop, we'll sample a batch from this buffer, minimize the difference between the left-hand side and right-hand side of the Bellman equation on this batch, and then repeat this some number of times. And then we could go out and collect more data. Of course, if we're doing offline RL, then we would skip that. So you can think of it graphically as you're going to interact with the world, pull in some transitions, some data basically, into this buffer. So you have this big bucket of transitions. And of course, they're typically connected into trajectories, but it kind of doesn't matter. And then you would crunch away on this big bucket of data to minimize the difference between the left-hand side and right-hand side of that Bellman equation. And then occasionally you'd go out and collect more data with exploration. But if you're doing offline RL, then you would skip that step. Of course, as an aside, in many cases, we would do offline learning and then do some additional online fine-tuning. So you might actually collect some online data after you're done with the offline phase. But for now, I want to focus on what happens in that offline phase. Okay, so we might look at this and say, okay, that's a pretty simple recipe. That's pretty nice. And there are lots of deep RL algorithms based on this idea, DQN, basically every actor critic algorithm that we like to use. So can we just do this? Like, is this all we need? We tried that. It can sometimes work, but it has a problem. So to my knowledge, one of the largest attempts to instantiate a QLearning system in actual real-world robotics tasks without any simulation, just from collecting real data, was this work called QT-opt back in 2018. And here the aim that we had was to basically try to see if we can take this recipe and we can really scale it up, and can we just get like really effective generalization to new tasks, new situations, that sort of thing. Basically reproduce the success of supervised learning with large data sets, but with off-policy RL. And this was a large-scale parallelized system that was essentially doing offline training, and then it was doing online fine-tuning with a continuous action version of QLearning called QT-opt. I'm not going to tell you that much about the system. I actually want to focus on what it teaches us about offline versus online RL. So this thing worked pretty well. So let me just play that video. It was pretty effective at picking up objects in dense clutter, small objects, big objects. Even when someone knocks the object out of the gripper, it would basically react to that and try to fix the mistake. So it exhibited some pretty interesting behaviors. And we put together a test set of objects that had not been seen anywhere in training. We wanted to see that it really had that generalization. But one of the things we tested while we were doing this is the difference between QT-opt, train on an offline data set, basically load up all the data from previous experiments and train on that, versus a version that was additionally fine-tuned with more online interaction. And the offline data set had 580,000 episodes, and the online fine-tuning added 28,000 more. So the amount of additional online data was very small by comparison, about 5%. So it's not the amount of data that's going to make the difference, but the fact that it was online. And this was the final success rate on this test set, 87% for offline, 96% for online. And you might say, okay, well, they're both pretty good, but this is a robotic grasping system. That's a very fundamental task, and you want a very high success rate. If you turn it around and look at the failure rate for the offline method is 3 times larger. So even though both systems worked, like we tried pretty hard, we wanted to make them work really well, the failure rate for the one that's purely offline is 3 times higher. So it's hard to explain that just with these additional 28,000 online transitions. So something is going on here. Something is not quite right with the simple recipe. A bit later, we wanted to have a more focused study of this problem. So I'm going to show you some experiments later, but I'll kind of present the punchline first. So that the punchline is that there's a fundamental challenge with offline RL that is not present in online methods, including off-policy online methods, including ones that cache data but still keep collecting more. And that's the problem, roughly speaking, of counterfactual queries. So if you have training data, and let's say you're learning to drive a car, and in the training data, the human drivers, they're not perfect. They make mistakes, but they don't make catastrophic mistakes. They never just swerve off the road randomly. And your policy wants to figure out, is it a good idea to turn left and go off the road into the bushes? Well, it's actually very difficult for the policy to answer that question using the data that was provided, because the humans in the data never did this. So is this good or is it bad? And how do you know if you didn't see it in the data? Online RL doesn't have to handle this, because in online RL, you can just assume that it's good, give it a try and see what happens, and then correct your mistake. But in offline RL, you have to make up your mind just from the data. So offline RL methods have to somehow account for these unseen out of distribution actions, ideally in a safe way, which means that they shouldn't assume that something that is totally unfamiliar might be good. But at the same time, they have to make use of generalization to come up with behaviors that are better than the best things seen in the data. So insofar as you believe you're generalizing, you should go with your prediction. But if you think you're going too far out of distribution, then be careful, because that might be a hypothesis that cannot be resolved using your data, and it might cause you to swerve off the road. So how does this problem show up? In 2019, 2 of my students, Aviral Kumar and Justin Fu, set up a little experiment to try to understand what goes wrong with offline RL. And this was sort of before the problems were really well understood. So they took a standard benchmark task, half cheetah, and they collected an offline data set. A good offline data set. It was actually just the replay buffer of an online RL run. And then they tried training on it with offline RL, and they found that performance would go up a little bit and then it would drop. And that looks a little bit like overfitting. So we thought, well, okay, let's add more data. That's how you deal with overfitting. So the blue curve here shows 1,000 data points. The red shows 1 million. And you can see there's no difference between them. They're equally bad. Good performance on half cheetah is around 10,000. This is getting minus 250. But we've got this Q function, and the Q function is trying to estimate the total reward that the policy will get. So we can ask the Q function, what do you think these policies will get? And that's the curve on the right, and it's a log scale. So that red curve, it's getting minus 250 reward. It thinks it's going to get 10 to the 7th power. Well, that's kind of strange. That is massive overestimation. It's like wildly, wildly optimistic. Like, it's going broke and it thinks it's going to win the lottery. That's not right. So this kind of stuff doesn't happen by accident. And it turns out that there's actually a mathematical reason for this that has to do with those counterfactual queries. So to understand the mathematical reason, we have to understand what distributional shift is. In a nutshell, it basically goes like this. If you are minimizing some loss on a data set, the data set comes from some distribution. So let's say that I'm just doing regression, f of x maps to y. And my training data is sampled from a distribution p of x. So this is called empirical risk minimization. I'm going to generate a data set from p of x, and I'll minimize the empirical risk and hope that that gives me an f of x that minimizes the true risk. And then we can ask a question. Given some new x star, is my learned f of x star going to be correct after I do this supervised learning? Well, that's actually a surprisingly tricky question. It might seem like the most basic question in all of machine learning, but it's not an easy question. So what you know is that if you didn't overfit, then the expected value of your loss is low. So if you had a big enough data set, you didn't overfit, the expected value of your loss will not be too high. In general, the expected value of your loss under some other distribution, p bar of x, that is not the same as p of x, might not be low. So you can only guarantee that it's low under the distribution you trained on. Now, what if x star is sampled from p of x? Well, even then, it's not necessarily the case that the error on x star is low. It's low in expectation, but x star might have been that one point on which you got unlucky. Okay, so this is a little bit tricky. Your performance depends on the distribution. Now, those of you who are deep learning practitioners, you might say, well, usually we don't worry about this because we're going to use neural nets. And neural nets are big and powerful, and they generalize well. So this is kind of stuff for mathematicians, not for real machine learners. And actually, I would kind of agree with that in most cases. So in supervised learning, the ability of good supervised models to generalize is remarkable. However, what if we don't just pick x star arbitrarily? What if we pick it to maximize the learned f of x? So it's picked with awareness of what f of x is. Now, this is really bad news. Imagine this green curve is the true function and the blue curve is your fit. Well, the blue curve is pretty good in most places, but if you pick the max, you might pull out exactly that point where f of x overestimates to the largest degree. You basically pick the largest positive error. It's like an adversarial example in a particular direction. So even if you think your model generalizes really well, if you're going to pick x star by maximizing your model, then you can always fool it. And that's what adversarial examples are. So that's actually really problematic. And that's what the problem in Q learning basically is. So let me just explain how that shows up in Q learning. Here's our Bellman equation again. And I'm going to write that Bellman equation a little bit differently. Instead of writing it as a max, I'll write it as an expected value under some distribution pi nu, where pi nu is that argmax policy. Pi nu is the policy that assigns a probability of 1 to the argmax. So I didn't actually change the equation. I just wrote it in a different way that makes it a little bit clearer that it's actually the expected value under some distribution. It just happens to be this argmax distribution. Now, when we run Q learning, we take the right-hand side of this Bellman equation as a target, and our objective is to minimize the error to that target under our training distribution. And our training distribution is this pi beta. So it's basically the data collected by this unknown behavior policy. It's our training set. So we would expect good accuracy. We would expect the Q function to be accurate in expectation under pi beta. So we expect this to be good when pi beta is equal to pi nu. But how often does that happen? The whole point is to find a pi nu that improves over pi beta. And even worse, we're going to pick pi nu to be the argmax. So that's exactly that maximization on the previous slide that is so problematic. And that's why we see that overestimation, because essentially that maximization in Q learning is finding these adversarial examples which produce erroneously large values. And then because we're running this repeatedly, we're iterating this, those errors compound more and more until you have massive overestimation. So that's basically the challenge with offline RL with value functions. I'll pause now and I'll take some questions. There are a few questions in the chat.
Okay.
All right, so the first question is, you mentioned that we could use other policies to collect some data, but in some scenarios for some data, the reward is sparse. What could be done in this case? Yeah, that's a good question. So generally, if you're doing offline RL, you do need to see data with rewards because, like, if nothing else, you need to know what the task is. I'll actually discuss a little bit later when I talk about evaluating offline RL methods that you can actually do a lot with data that does not have rewards. But you can't succeed if you don't have any data with rewards. rewards. So it's okay if you have lots of data with 0 reward and just a little bit of data with a positive reward, but you need some rewards in there. The second question is, you mentioned that we might be faced with a counterfactual situation. How do we go about collecting this type of data in this situation? Alternatively, can we use algorithms related to causal inference to solve these kinds of problems? Okay, that's a very good question. So the methods that I will present as solutions to this issue, what they basically try to do is they try to, roughly speaking, they try to guess what kinds of counterfactual queries are you capable of answering and what kind can you not answer. And for the ones that you can't answer, just don't go there. Just don't take those actions. And that's kind of the best you can do if you can't collect more data. Like if the data just doesn't support answering some question, then you can't answer that question. So you just have to stay away from there. Of course, if you're allowed some additional online data collection, you could be really smart and try to probe the environment to answer those. In terms of methods from causal inference, I think that's very possible. So generally, there's like, a bit of a discrepancy in terms of the problem setup. So folks who deal with causal inference typically deal with much more structured systems that have relationships between random variables that are characterized, whereas in RL we basically have one graphical model, which is the MDP, and that's what we always use. But I do think that some of those ideas could be imported into offline RL, and I think that's a kind of a promising direction to look into for future work. All right, next question. For humans to understand the world, we need to understand causality. So will causality analysis help the RL algorithm for better sample efficiency or better understanding of the real world? Yeah, so that's kind of similar to the previous question. I think that's very possible. So the methods I'm going to discuss now, they basically almost like sidestep the issues of causality by just basically staying away from anything that might incur too much distributional shift. But you could probably do something smarter and actually, break apart the system, look at the interactions between the variables, and actually tease out some of those relationships. And that might work better if you get that structure. How do we know that the Q function is unique to begin with? So if you have no function approximation, then there is a unique solution. In general, when we're doing deep RL, we have function approximators and all that stuff. So there, we can't guarantee it. And typically what we're concerned with is getting a Q function that is good enough. So something that sufficiently minimizes error and leads to a good enough policy. But this is actually a very complicated question in RL theory. Okay, so let me proceed. So I talked about how we have this overestimation problem, and it's due to the maximization, which incurs distributional shift. So next, I'm going to discuss how we can address this problem. How do we design offline RL algorithms to basically mitigate this issue? So one very classic type of method for addressing this basically modifies the formula from before, where instead of pi nu being selected just to maximize the Q function, we're going to have some kind of constrained process. We're going to select pi nu to maximize the Q function, but also subject it to a constraint that limits how far it can deviate from the behavior policy. So the constraint, roughly speaking, just directly limits the amount of distributional shift that you're allowed to have. And this kind of solves distributional shift, right? Which means no more erroneous values. Well, kind of. So this is a classic class of approaches. There isn't really a single name for it, but I call them policy constraint methods in my tutorial. Other people call them different things, but I think policy constraint is a pretty good name for this. And it's a very old idea. As far as I know, it doesn't have any single name, but it goes back to work by Todorov, Kaplan, and many others. Trust regions and covariant policy gradients are actually based on this idea, and it's used in some more recent papers, including papers for offline RL. But it has a few issues. One of the issues with this type of approach is that in order to calculate that constraint explicitly, we typically need to know the behavior policy. Like you need to know what you're constraining against. And if the data comes from very heterogeneous sources like human data from hand design controllers, random data, many different sources, it might actually be very hard to know what pi beta is. It might even be very hard to estimate it because it might be some very complex multimodal monster. Like it might actually be easier to learn a good policy than to learn what pi beta is. And the second issue is that this procedure can be both too pessimistic and not pessimistic enough. So to understand what I mean, let's imagine that it's a KL divergence constraint like I have written here. And let's say pi beta is uniformly random. Well, if you enforce a KL divergence constraint against a uniformly random policy, that basically says you're limited in how deterministic you can be. And that's very strange. Like, just because your data is random, that means that your policy also needs to be random. Well, it doesn't seem right. Like, it seems like you should be able to pick the best deterministic action within the support of the data set, instead of limiting yourself to be random just because your data is random. And at the same time, it might be not pessimistic enough. So you might have a small KL divergence and yet still put a lot of probability mass on something that's kind of out on the fringe. So it's not a bad strategy, but it's not a great strategy. And we can do a lot better. So there are two principles that kind of change up this idea a little bit that we found to work really well. One principle is to design algorithms that avoid ever having to evaluate actions that are not in the data set. It's a little tricky to do this, but if you can do this, then you will avoid the distributional shift problem. Of course, you have to do this while still improving over the behaviors in the data set, and that's a little tricky, and you have to use the generalization power of neural nets to enable that. So the idea is that if these are our training points, well, whatever we fit to those training points might be pretty crazy outside of the training points, but at the training points, it's going to be pretty good. So it might have these erroneous peaks, but as long as you don't go there, you're fine. Option 2 is to train the Q function explicitly so that these out-of-distribution actions are never too big. You can't force the out-of-distribution actions to be correct because you don't know the right answer there, but you can at least force them to not be too big. So this is kind of almost like an adversarial training style approach. Basically, find these peaks and crush them. It might mean the value is incorrect, but at least it won't be too high. Both of these options can work pretty well. So I'll tell you about both of them and some algorithms we've developed that basically instantiate these ideas. So for option 1, I'll start with a paper called Accelerating Online Reinforcement Learning with Offline Datasets by Ashwin Nair that introduced an algorithm called AWAKE, AWAC. So AWAKE is actually a policy constraint method, but it's a policy constraint method that avoids the need to model the behavior policy. So the trouble is that when you run a classic maximization without any constraint, then you're going to query the Q function with actions that are not in the data set. And that means that you're going to train the actor on potentially adversarial actions. So you want to somehow modify this so you train the actor for that second step without querying out of distribution actions. How can you do this? Well, here's an idea. What if we train the actor with some kind of weighted regression? So here is a maximum likelihood loss. Train the actor to maximize the log probability of the actions in the data set. That's not quite right because that's not necessarily going to maximize your Q value. They'll just copy the data. But what if you put in a weight and you somehow select this weight so that actions for which the Q value is large have a larger weight? So now you will preferentially copy the good actions and not the bad ones. And you could imagine that maybe if you choose those weights very carefully, that will effectively maximize your Q values. And it turns out that's true. So actions with larger Q will have higher weight. And in fact, there's an interesting derivation where we can show that if we select that weight to be proportional to the exponential of the Q values divided by some temperature, then that will exactly provide the solution in the absence of sampling error to the constrained Q value maximization. This is exactly that constraint policy update, but now we've done it without having to know what the behavior policy is, just by using samples from the behavior policy and weighting those samples by the exponential of the Q values. So that's pretty cool. Now, it's still a policy constraint method. It's just one that doesn't require knowing pi beta. So we've gotten rid of one of the issues, but not the other one. And it's straightforward to prove that this is the case via Lagrangian duality. I won't go into that because I don't want to kind of bore you with walls of math, but it's a pretty neat derivation. So this gets us a constraint policy update without knowing pi beta. So this is the basis of an algorithm called advantage weighted actor critic. So here I just substituted in the equation for the weights into that max likelihood equation. And this turns out to be a pretty good way to do offline pre-training followed by online fine-tuning. It's not actually the best algorithm for just offline training. There are many better algorithms, but it's pretty nice for doing fine-tuning because the same objective also works decently in online mode. Here's a kind of a video showing some examples of this. So what you're going to see here is a prior data set that consists of kind of suboptimal demonstrations for opening a door. If you do offline training, you get to 24% with advantage weighted actor critic. And if you then do additional online fine-tuning, then it gets it up to 88%. So it works pretty well for online fine-tuning, not great for pure offline training. Okay, so I'll skip the graph. But so far, we talked only about the actor part of the problem. Can we also avoid all out-of-distribution actions in the Q function update? Well, here's an idea of how to do it. In the Q function update, the out-of-distribution actions can happen because of these target values, right? We need to plug some action into the Q function, and if we plug in an action that we sample from our actor, that action might be out of distribution. Now, if the actor obeys the constraint, and maybe at convergence, it won't be out of distribution, but in the middle of training, it might not even obey that constraint very well, and we might get these nasty actions. So this target value is basically the value function evaluated at the next state. So what if we just separately represent the value function as just another neural network? And we're going to train the value function by regressing onto the Q function at our sampled states and actions. So we'll take all the states and actions in our data set, and we'll just regress V of SI onto Q of SI AI with some loss function L. So for example, we might use mean squared error loss. That's not very good, of course, because if we just do that, then we're basically ignoring our new policy. Like we can train V this way, but the action here in our data set, it comes from pi beta, not from pi nu. So that's not good. That's not going to give us an optimal Q function. It'll just give us the Q function of the behavior policy. But we can change the loss function to fix this without needing to actually query out of distribution actions. So here's the idea. Let's say that you have a bunch of different trajectories, and let's consider this state, the one indicated in green. That state has only been seen once because you have a large continuous state space, but you've seen other similar states nearby. So those other trajectories above and below, they don't visit the same exact state, but they visit similar states. So you might surmise that those similar states probably have similar values. Not the same, but pretty similar. But in the data set, different actions are taken at those states. So what that means is that if you consider a state and other states that are similar to it, the Q values for the corresponding actions, in some sense, illustrate the distribution of different Q values you might get if you take different actions. You can think of this distribution as a kind of histogram, where the horizontal axis is the value and the vertical axis is the frequency of seeing that value. Now, it's not literally a frequency because, of course, each state is only seen once, but if we're doing all of this with neural nets kind of generalize. So you could imagine that in the neighborhood of that state, there's actually a variety of different values. And the reason that those values vary is primarily because in the data set, different actions were taken at those states. So the reason that this is a distribution, the source of randomness, is actually the difference in actions. Okay? So the mean squared error loss is going to pull out the mean of this distribution. Well, what if instead of pulling out the mean, we pull out something like an upper quantile, the upper end of this distribution? The upper end of this distribution basically corresponds to the kinds of values we might get if we take good actions, actions with high value. That's the value of the best policy supported by the data. So that's what we're going to do. We're going to actually modify our loss function so that it picks out the upper end of this distribution. And a particularly convenient loss function for doing this is something called an expectile loss. You can roughly think of expectiles as very much like quantiles, only for quantiles, you take linear intervals. With expectiles, it's quadratic. But the nice thing about expectiles is that there's a very simple loss function that will give you an upper expectile. So if you want the expectile tau, then you simply use this kind of asymmetric mean squared error loss. So the regular mean squared error loss, it's like a parabola, right? So it's symmetric on both the negative and the positive branch. This expectile loss that I have here is asymmetric. So it punishes positive errors less than negative errors, which means that it's going to favor the upper end of this distribution. And it turns out that we can actually show that if you use this kind of expectile loss, the value that you will get will, in the limit, look like the max over the actions that are within the support of the data. So that's pretty cool. We're basically finding the value of the best actions that are in the support of the data by doing this. And to accomplish it, we're leveraging the ability of neural nets to generalize, the ability of neural nets to realize that other nearby states should have similar values. And therefore, this induces a distribution over values. And these loss functions do not involve any actions that are not in the data set anywhere at all. So if we use this L2 tau for a big tau, then you will get this maximization effect. And that's the basis for a method called implicit Q learning, developed by Ilya Kosterikov. And the idea in implicit Q learning is to basically have a Q function and a separate value function. The Q function is just trained with regression onto R plus V, and the value function is trained with this expectile loss. And the theoretical result shows that this performs this in distribution maximization, and therefore is like a distribution constrained version of Q learning. But implementation wise, it doesn't involve the max at all. It just involves this expectile loss. So this means that there's essentially an implicit policy. That's why we call it implicit Q learning, because the policy doesn't actually show up in the training at all, but it's implicit, implicit in the use of that expectile loss. So now we can do value function updates without ever risking out of distribution actions. Now, before I talk about the results for this, I'm going to cover option 2, the other class of methods that seem to work well, and then I'll talk about how we evaluate these methods and present the results. Okay, so option 2 that I mentioned before is to train the Q function to avoid out of distribution errors altogether. So actually patch the mistakes in the Q function. So remember, the problem is this overestimation. So what we can do is we can basically find these peaks and push them down. One way we can do this is we can take our original objective, our regular Bellman error loss, and we can augment it with a regularizer that pushes down on big Q values. So if you look at this term, what it's doing is it's minimizing the Q function in expectation under actions from a distribution mu, which is trying to maximize the Q values. So mu basically hunts down these large Q values, and the regularizer pushes them down. And it turns out that if you use this regularizer with an appropriate weight alpha, you can actually prove that the resulting Q function lower bounds the true Q function for that policy, which means that it eliminates overestimation if you choose the hyperparameters carefully. In reality, the full conservative Q learning algorithm based on this idea, and this is an algorithm developed by Aviral Kumar, derives a better bound. So in the full conservative Q learning algorithm, we don't just minimize the Q values, we also added another term that pushes them up on the actions in the data set. Now, this might seem like a very strange thing to do. Like, why would you want to push down on some actions and push up on others if your goal is to fix overestimation? But let's think about what this will do to your behavior. If you would like your policy to stick to in-distribution actions, then if you make the value of the in-distribution actions larger and the value of the out-of-distribution actions lower, then you'll push the policy back in distribution. But when you do that, eventually all the big values will be in distribution. So eventually mu will also pick up on actions that are close to the data set. And at that point, these two terms basically balance out. So if you're in distribution, you're pushing down on the stuff in the data distribution and you're pushing up on it. So that cancels out. But if you're out of distribution, then you're pushing down on the place where you're at and you're pushing up back in the data. So that'll move you back towards the data. So that's pretty cool because once you're in distribution, the term just vanishes and that reduces the bias that you incur. You're no longer guaranteed to lower bound the true Q function for all states and actions, but it turns out that you're still guaranteed to lower bound the expected Q value under your policy, which is all you really want because the goal is to avoid overestimating the value of your policy. So it still gives us a very appealing guarantee. Okay, so those are the methods, and now I'll talk about how we can evaluate them. So before I present the results, I want to talk a little bit about the kinds of tasks that we can use to understand if our offline RL methods work. Of course, ultimately, in the long run, we have particular tasks that we want to solve. You want to solve maybe inventory management, stock trading, autonomous vehicles. But in the meantime, we need some evaluations. Okay, there's a question in the chat. Can we design a meta-learning strategy to accumulate parameters from previous online, offline states to help OOD actions? Or these algorithms like IQL or CQL are already involving kind of a meta-learning strategy or meta-RL or meta-continuous learning? Yeah, let me think about how to answer that. So generally, meta-learning methods, conventionally, meta-learning methods require having multiple tasks. So everything I'm covering so far is in the single task setting. Now, it can be extended into the multitask setting, and we can, in fact, devise offline meta-RL methods. But typically, switching to meta-learning only exacerbates the distributional shift problems because meta learning methods, they need to interpret the context, the experience from the new task, and that also can experience distributional shift. So generally, switching over to meta learning just introduces more distributional shift problems. They're interesting problems, and we can devise algorithms to tackle them, but it doesn't really make things easier, from my experience. There's another question. Do you think an enlarged state space, multimodal input, might help tackle the OOD problem? For example, we know that humans can guess the consequence of counterfactual actions based on their knowledge. So could this be possible for machines? The trouble is that the particular out of distribution problem that we're dealing with here, here is out of distribution actions. So you can think of them roughly as adversarial examples, right? No matter how powerful your model is, it's not going to be robust adversarial examples unless you do something about it. And while adding more input information or making the model bigger or making it more powerful will help it be more accurate, it won't actually help with adversarial things like this. So if you're maximizing against your function, you really need some algorithmic modification to patch that hole. It's not enough to just make the model more powerful or give it more inputs. Yeah, any other questions?
Excuse me. So in this term for the estimated Q pi on the CQL, why are we adding the bound at the end, like the objective?
Why are we adding what at the end? Sorry, I just didn't hear you. Why are we adding what?
We're adding the objective. Sure. So for the CQL, why are we adding the objective function at the end?
Oh, you mean the second line?
This last term, yeah.
Yeah. Well, so that's just the Q learning objective. So that's what ensures that your Q values are actually good Q values. So basically, that second line, that's what you would use in regular Q learning. And our aim here is to modify it to avoid those out of distribution things. So this is the entire algorithm, basically. The first line is the regularizer, and the second line is the thing that actually does the Q learning.
I see. Okay, thank you.
All right, thank you all for the questions. All right, so let me talk about evaluation. So first question, what do we expect offline RL methods to actually do? That's a surprisingly subtle question. So one bit of intuition, which I think is bad intuition, is that maybe offline RL is like imitation learning. So maybe you get some data and you want to recover a policy that basically does what the data does. I think that's bad intuition because we want actually a lot more than that. Although it can actually be shown that even in this setting, offline RL can improve over imitation learning, but for somewhat subtle theoretical reasons. The better intuition is that it's about getting order from chaos. It's about the case where you have a bunch of data that is not necessarily very good, but somehow inside that data, you can find a policy that is better. So maybe you can combine the best parts of a bunch of different trajectories and get a better trajectory. One very simple intuitive example is this kind of stitching example. So if you have examples in your data set of going from A to B and other examples of going from B to C, maybe you can figure out how to go from A to C. So you can basically combine these things together. But that's a very crude example. In reality, you might be doing this kind of stitching everywhere all at once. So imagine that you have data from 1,000 different humans doing stock trading, and each of them is good at something and bad at something else. Well, then you can pull out the best parts of each of them and get a superhuman policy out of that. So that's kind of the intuition behind what these methods should be doing. If you have an algorithm that can properly perform dynamic programming, you can take this idea much further and get near optimal policies from highly suboptimal data by basically pulling out the good part of every trajectory, the good part of every part of the data set. So here's an example just to kind of get you thinking about what can be done with this. This is a robotics example. And here the goal is to pick up an object, to pick up this ball from a drawer. But at test time, we're going to change the scene in some way. Maybe we close the drawer. Now, of course, if the robot only learned how to pick up the ball from an open drawer, it has no way of knowing how to pick it up from a closed drawer. But what if we have prior data? And that prior data shows a variety of other skills. none of the prior data has picking up the ball from the drawer, but it has opening the drawer, it has closing the drawer, it has moving other objects, maybe moving other drawers, and all of this data has a reward of 0. So there's the only data with a non-zero reward is picking up from the open drawer. Well, a good offline RL algorithm should be able to figure out that the state where the drawer is open is a good state with a high value, and that high value will be propagated to all that prior data, even though it all has rewards of 0. And the algorithm will figure out that opening a drawer is a good idea because it leads to a high value state where the drawer is open and you can pick up the ball. So if you take this data where there's not a single episode that shows opening and picking up the ball, you can get a policy that will pick up the ball from an open drawer, but also a policy that will open the drawer and then pick up the ball, and a policy that will close the top drawer, open the bottom one, and then pick up the ball, and a policy that will take an obstruction, pick it up, put it away, then open the drawer, and then pick up the ball, without ever having seen a complete trajectory that does all of this together. So this is basically that stitching idea in action. All right, so when we evaluate offline RL algorithms, of course, we use benchmark tasks. And a very popular class of benchmark tasks is the D4RL dataset. And D4RL includes a variety of tasks. It includes standard Mujoko Gym style locomotion tasks with datasets of varying quality, expert, medium, random. It also includes these maze tasks, and the maze tasks are specifically intended to test ability to stitch, ability to combine parts of trajectories. So in the maze tasks, the goal is to go from the lower left corner to the upper right corner, but there isn't a single trajectory in the data set that actually does this. There are trajectories that go between other pairs of points, and you're supposed to stitch them together to figure out how to perform the task. So the best trajectory in the data set is very bad, but if you combine the best parts, then you can be very good. And then there are kind of application-centric tasks like dexterous manipulation, controlling a robotic arm, traffic control, autonomous driving, and so on. So the gym-style locomotion tasks, they're kind of simple diagnostic tasks, and they don't really test this compositionality. They're not really testing stitching. They're mostly testing your ability to basically imitate the best part of the data set. The maze tasks really test the compositionality of your method. And then these other tasks are basically application tasks. So it's interesting to look at the differences between the locomotion tasks and the maze tasks, which are the ones that kind of are meant to test compositionality. So here are results for a variety of methods. Let me tell you about which ones these are. So we have the first three. They're basically kind of behavior cloning style methods. Regular behavior cloning of the best 10%, and then decision transformers, which is basically like a fancy behavior cloning method with transformer models. Then we have some recent offline RL methods, one-step RL and TD3 plus BC, which I didn't cover. Then we have advantage-weighted actor critic, which I talked about, and that's that method that's not very good for offline RL, but it's pretty good for fine-tuning. And then we have CQL and IQL. So what you can see in the results here is that most methods get similar results to good behavior cloning implementations on the gym locomotion tasks. So you can see like 10% BC is 666, and then like CQL and IQL are 690 plus, but kind of in the same ballpark. On the other hand, for those maze tasks, the ones that actually require compositionality, there's a much bigger difference. So you can see that CQL and IQL are 2 to 3 times better than the behavior cloning based methods. And that really suggests that dynamic programming, appropriately using value-based RL, is really important for these tasks. So these tasks really benefit from compositionality. So, one takeaway from this is that these methods work pretty well. The other one is that we have to be careful when we evaluate offline RL methods because it can do things that imitation learning simply can't, like chain together the good parts of highly suboptimal data, but you need to test the right thing in order to measure that. Here's a comparison on fine tuning. So here the number to the left of the arrow is the one after offline training. The one to the right of the arrow is after online fine tuning. And you can see that advantage weighted actor critic improves a lot during fine tuning, but it starts off pretty low. So it's not a very good offline RL method, but it's a good fine tuning method. CQL starts off pretty high, but it doesn't improve very much. Whereas IQL starts off pretty high and then improves a fair bit. So it's actually a very good choice for online fine tuning. So I talked about these two options. Avoid ever evaluating actions that are not in the data set, and option 2, train the Q function so that auto distribution actions never have high values. There's actually a little bit of reverse chronology here. Option 1, IQL, that's actually a very recent paper in 2021. Option 2, CQL, is a bit older, but it was a little more logical for me to present them in the opposite order. In terms of the trade-offs between them, CQL has fewer hyperparameters, cleaner workflows with offline fine tuning. So we actually have quite a bit of theory about CQL, and we know how to adjust hyperparameters. IQL is newer, and we have kind of less understanding there. But IQL seemed to perform slightly better and significantly better during fine tuning. So that's kind of the takeaways as far as how the methods compare. We still don't know which principles are going to be more effective in the long run, but so far these are the two options that seem to work pretty well. All right, so there's a question in the chat. In advantage weighted actor critic, is it possible to choose different formula for weights instead of the exponential to achieve the similar performance? Yes, that's a very good question. So there's actually a concurrent paper that came out, I think, like a week later than Awake from a group at DeepMind called CRR. And it's basically the same, except that it uses a different weighting scheme where instead of doing the exponential weighting, they actually do hard thresholding. So they pick like the top something percent. I think it's like the top 10% or top 20% or something. And they just put a weight of 1 on that and 0 on everything else. And that can actually be pretty good, because if you do that hard thresholding, it's a little bit less principled. It doesn't have the nice interpretation as a KL divergence constraint, but it simplifies hyperparameter tuning. So it can work better in some cases. So in general, there are a variety of weighting schemes. Exponential is kind of the most principled one, but other schemes can be easier to use. Since there are similarities with supervised learning, is there an analog of cross-validation in offline RL? That is a very, very good question. So the short answer is no, but we are trying to do that. So we actually have a paper in Coral 2021 on workflows for offline reinforcement learning, where we propose a few metrics that are they're not quite as clean as validation error, but they have kind of a similar flavor. So in general, it's very hard to get something that is as clean and as beautiful as validation error, but there are sort of secondary metrics you can use. You just don't get one metric. You have to look at multiple metrics to figure out whether you need to increase capacity or decrease capacity. And by the way, I think this is a really important area of research. So if you're interested in notions of validation error for offline RL, very good topic to work on. All right. Let me just briefly conclude with some discussion of applications of offline RL methods, just to kind of give you a sense for why this kind of stuff can be so useful. So to try to explain the power of offline RL, let me tell you about, well, this is kind of part of why I really like it, because it actually makes my research less painful. So of course, in my group, my students and I do a lot of research on real world reinforcement learning. Real world for us means with real world robots. And with online RL, our process looks something like this. Step 1 is to instrument the task so that we can run reinforcement learning. So if this is in the real world, it literally means building some kind of contraption to provide a safety mechanism, some mechanism to facilitate autonomous data collection. So if you have a robot that needs to try a task multiple times, it needs to reset between attempts. If you have a vehicle, you need to manually code up some kind of safety mechanism so that it doesn't collide. Implement some code to evaluate rewards, resets, etc. And then you wait for a really long time for online RL to run. And you're not actually just waiting. During that time, you might actually be doing some work, because maybe your system gets into some awkward state. And if you go in and manually fix it up, manually put it back so they can try again. And after that really long process, it doesn't work. And then you change the algorithm in some small way and run the whole process again. And that can be very time consuming. And in practice, because it's so time consuming, we run small, short experiments with small data sets that don't generalize very well. And furthermore, once you're done with all this, if you want to do it again for another task, you throw it all away and you start over for the next task you want to do. So as you can guess, this is a very manual and very painful process. With offline RL, the process is different. You collect your initial data set, which can come from a variety of sources. You train your policy offline. And if you want to change your algorithm, you just run the algorithm again. And if you feel like you need more data, you go collect just a little bit more data and you add it to an ever-growing data set. So this is all much less painful. And once you're done, once you got it to work, you can keep the data set and use it again for the next project. So you don't have to even start from scratch the next time around. So that makes things a lot easier to do, a lot easier to iterate, a lot easier to make progress. So I'll tell you about a couple examples of projects that we've done in robotics that basically take advantage of this recipe. So at Google, we had several projects that basically involved large-scale data collection for robotic manipulation, QT-opt, MT-opt. So these are both papers that involved months of data collection with multiple robots many different tasks, thousands of objects. And then later on, we had a new hypothesis. We thought, well, can we learn these tasks without any manually specified rewards using goal-conditioned RL? This talk is not about goal-conditioned RL, and it doesn't really matter what our hypothesis was. The point is that we wanted to resolve this hypothesis without months of data collection. So of course, what we did is we set up our goal-conditioned RL algorithm, and then we just ran it as an offline RL algorithm using the same exact data without a single additional trial of data collection. And that actually ended up working pretty well. So this is the goal conditioned system. The lower right image is the goal. There's no reward function. The task is defined entirely using the goal image, and it uses a variant of CQL for training. One of the cool things about this method is that once you train this goal conditioned thing offline, it serves as a kind of unsupervised pre-training for downstream RL. So you can do offline unsupervised RL with this goal system, and it's almost like kind of a BERT-like model for robotic RL. So you pre-train on all the data you've got, and then you're given a task, a real reward task that you learn online. And if you utilize this goal condition thing to accelerate it, then you can learn that new task much more quickly because the offline data with goal condition RL kind of puts a lot of knowledge about the world into the model already right from the start. So that's pretty cool. We could do this without collecting any additional new data for the goal condition phase. Another example. In 2020, my student Gregory Kahn collected 40 hours of data for a ground robot navigating Richmond Field Station. In late 2020, Dhruv Shah, another PhD student, a very lucky PhD student because he could just reuse Greg's data, took all this data and he trained a goal-conditioned system for doing inspection tasks and delivery tasks on the same data set without any data collection, and it worked out of the box. I mean, obviously, you have to iterate on it. You have to debug the algorithm, but he didn't have to go and collect more data. So it was a lot easier to do this research building on the data set that was already collected. And in 2021, Dhruv Shah used that same data set to devise a system that could learn to explore new environments effectively, to kind of to search for goals in a new setting. Again, using the same data. And this kind of accelerates the research. It creates momentum where once you've got that data set, you keep building on it, and every subsequent research project is actually easier and generalizes more broadly. All right, so I'll take a couple of questions now. Since you mentioned autonomous driving earlier, I wonder what is your take on applying offline RL for the driving problem? It seems pretty easy to collect large amounts of human expert trajectories, but hard to collect bad data. So in this case, do you think offline RL may degenerate to imitation learning? That's a very good question. So I think it depends a little bit on what you want. So if you just want to do what the humans did, then yeah, I mean, imitation learning is a pretty good choice. But you might want to do something that is better than human drivers. Maybe all the drivers that collected your data in your data set, they were good in some places, but bad in others. And maybe you want a superhuman driver, a driver that drives in a superhumanly safe way or a superhumanly comfortable way. As long as you can measure that quantity, as long as you can label your data set, in principle, you could use offline RL to try to get that. Now, of course, whether that would work in practice or not depends on a bunch of details. I mean, driving is a very difficult problem. You need to deal with high dimensional observations. You need to deal with long tail distributions. And those challenges don't go away just because we switched to offline RL. But in principle, you could do better than imitation by basically being the best of any human in any situation. So if some humans are good in some place, some are good in others, you'll be the best of that if offline RL works. All right, next question. Okay, so this is a follow-up to the one before. What I actually mean is maybe we can acquire knowledge without actually having to take the actions, but instead learn the situations from natural language videos, and not just in the form of calculating the rules in inverse kinematics, but in the way pre-trained models like BERT are doing, trying to understand the consequences using statistics. Okay, I think I see what you're getting at. So I think that's a very interesting idea. And I think that in principle, if we're careful about dealing with domain shift, with the fact that videos and so on are not in the same domain as the task that you're actually learning, I do think that it could be quite interesting to think about how perhaps an offline RL algorithm could be run on heterogeneous data from a variety of sources to acquire a better understanding of the world. I think that's actually like a really nice potential future direction for research in this area. I'm not aware of anyone that has done this yet, although there's been some experimentation running RL on videos without action. So this is kind of the setup there. It's typically there's some data from a robot, and there's some video data, and somehow there's a bit of domain adaptation to put those in correspondence, and the video data is included in the replay buffer for the RL process. And people have done a little bit of that, but doing it at a kind of a larger scale, as you're suggesting, could be really interesting. What did you think of the relation between causal inference and RL? How can we combine the two things? As far as I know, there are some scientists researching causal reinforcement learning. Yes, so I think that combining these concepts is a good idea. I don't think I can say much more than that because, I think that has to get into the details, and I don't know how to combine them. But I do think that they're very related, and I think very likely concepts from causal inference can enter into how we calculate the value function updates, and maybe that could lead to a better class of offline RL methods. So I think that's very promising, but I don't have anything more intelligent to say. Like, someone has to figure it out. All right, next question. Can the methods you mentioned for offline RL, distribution shift, be generalized to online RL as well? Yes, that's a very good question. So basically, if I'm understanding correctly, what this question gets at is that, well, this kind of distribution shift is not exclusive to offline RL. It can also happen if you're doing online RL, but you just train for many, many gradient steps. So if you want to be as sample efficient as possible, you could essentially imagine that every single time you collect a new data point, you run offline RL basically. And then you run it again when you collect another data point. And that's, of course, pretty extreme, but you can imagine less extreme versions of that. And I think the answer is yes. I think that would be a really good idea. One word of caution there, though. A lot of the methods we use to mitigate distributional shift make the algorithm more pessimistic. Like CQL literally minimizes Q values at OOD points, which is good in the offline setting. But if you're doing online RL, it can fight back against exploration. It can make you bad at exploring. So if you want to use offline RL ideas in an online setting, it's probably a good idea, but you have to somehow fix the exploration problem. Maybe add more exploration bonuses or something like that, because otherwise you might not explore enough. Okay. And by the way, I'm nearly at the end of my talk, so this is a good time for questions. I don't really have anything particularly interesting after this. All right, next question is, several years ago, I learned the robotics engineering before. We also tried evolution algorithms or RL. There is a thing called the reality gap. How can we really solve this? Pure online and onboard learning is hard, especially for a group of robots. Only using offline RL and trying to use the data sets time and time again will be enough. And also we need to collect enough data and update them in time. Can we find a more efficient way for this problem? Offline RL seems more like a trade-off, or basing on the great computing and data processing capability that we can take more easily. Okay, I see. Well, so that there are a few things wrapped up in that question. So I think partly this question is similar to the previous one about incorporating offline RL ideas into online RL. And I think their offline RL concepts can make online learning more efficient because you can take more gradient steps. But I think there's something a little more complex here in regard to things like the reality gap and pure online learning being hard. I think that there's kind of a difference of approach here. So we could take the approach where we do try to get learning to work well in simulation, and then maybe we incorporate some real data as offline data. Or we can take the approach where we just rely entirely on data from the real world and then use offline learning to basically make it tractable, make it practical to do. I think the latter is actually very promising, but I think that partly there's a bootstrap problem. Like if you have a large data set already, then offline learning is a great choice. If you don't have a large data set already, then maybe simulation is a good choice to bootstrap the whole process. Okay.
Sergey, do you mind go back a little bit? Because I think you missed 2 questions. And,
oh, did I?
Yeah, so that we don't get a piles of more questions.
Sure.
So it should be the question from Z, like 8:04 p.m. So Zhang Xi, yeah.
Okay, maybe I'm not seeing it. Would you mind reading out the question to me?
Yeah. So let me see how to read this. Or the person asked a question. Are you there? So how does this method relate to stationary distribution correction in off-policy evaluation or off-policy evaluation? OPP?
Okay, yeah.
Okay.
So what this question is getting at is that there are methods for off-policy evaluation that essentially try to estimate the distribution that you would get with a new policy, and either estimate an importance weight for it or just directly estimate the distribution. And the algorithms that I described generally don't try to do that. So the difference is that in off-policy evaluation, if you want to figure out the distribution of the new policy, what you want is a state distribution. You want to figure out the state distribution of the new policy and then use it typically to derive a weight and then do a weighted average of the rewards in your data set. All the methods that I talked about actually don't account for state distribution shift at all. They're only accounting for action distribution shift. Now, we could also account for state distribution shift, and that would probably make them better. But from my experience, action distribution shift is much more of a problem if you're trying to learn a good Q function. And in fact, there's actually some recent work that shows that learning a Q function or a value function can also be a very effective way to do off-policy evaluation. It's harder to make theoretical kind of guarantees about it, but it can actually work better than estimating the distribution of the new policy. So there's a, I'm blanking on the author's name, but there's a group at DeepMind that works on this, and they had a paper on using fit Q iteration to evaluate policies and show that it actually works pretty well. But yeah, the direct answer to your question is the stationary distribution stuff is about state distributions, and nothing here deals with state distributions.
Thank you. The next question is the weight definition of AWAC is similar to the optimal policy expression in maximum entropy RL. Do they have any connection?
Yes, absolutely. So basically, you can think of max entropy RL as minimizing KL divergence to the uniform distribution, whereas the KL divergence constraint in awake minimizes KL divergence to the behavior policy. And the only difference between those, they both have an entropy term. It's just that this one also has a log pi beta term. So they're actually quite related.
Thank you. So the last one that you missed is offline RL training for unsupervised setting or for multitask setting.
Yeah, it's good. We should do it. We should do more of it. Is there more to the question, or is it just like, can we do this?
Yeah, I think you have just my question. I just noticed your paper. This one is a conservative data sharing for multitask offline reinforcement.
By Tianhe Yu. So Tianhe is doing really good work in this area. So this is, I think it's a really fascinating area, and I think there's a lot of interesting stuff that we can do. It's very natural because when like a good way to get lots of data is to basically take it from other tasks. So it's very natural to study this.
Right. Because I'm quite interested about the multitasking learning. This kind. Okay. Anyway, I will read your paper. Probably I can ask more questions later for you. Thank you.
Yeah, sounds good.
Yeah.
All right.
I have a question.
Go ahead.
So option 1 and option 2 both seem excessively risk averse, because there might be actions that are not in the data that actually have a high reward and you want to take them. So how about option 3, which is you have a fear of the unknown term in the reward function. So you're controlling your robot or whatever to avoid being in situations that are, seen, where your uncertainty is high, if you quantify it, and then, there's a trade-off between that and, trying to do what you think will bring a lot of reward.
So it's actually very similar. But I think what you're insinuating is, if I understood you correctly, is you have this fear of the unknown, like when you're actually running in the real world, like not when you're training. Is that what you're getting at?
Well, yes, but it's based on what I learned. It's really when I'm in the present, based on what I've learned in the past, right? So there's,
So I think actually the option 2, the conservative Q learning method, it actually does something very similar, but indirectly, because the issue is that you need to have fear of the unknown, not just at runtime, but also when you're training, because when you're training, a Q learning method is essentially doing planning at training time. So it's basically thinking like, what are other options I might take, back them up, incorporate them to the Q function, and then back up the next thing. So if you start backing up garbage from potentially risky transitions, then that garbage will build up. But there's actually an interpretation of CQL, a theoretical interpretation, that shows that it is actually very similar in some ways to basically adding essentially a penalty for unfamiliar actions. So it's actually conceptually very similar to fear of the unknown, but at training.
I agree. I agree that option 2 approximates option 3, right? but in a way it's mixing up two different things, right? One is whether an action has high reward. Another one is where you're in a situation that there's a lot of uncertainty about what your reward will be.
So one way that we can see how they're similar is that the actual loss function here is very similar to what we would use to train an energy-based model. So in an energy-based model, what we would do is we would find points with low energy, and we would raise their energy. And then we would take points in the data set and we would lower their energy. And that's more or less exactly what the loss here is doing. It's taking points in the data set and raising, just with the opposite sign. It's taking points in the data set and raising their Q, taking points that have a high Q and lowering their Q. So in effect, it's acting a lot like a density estimator. So it's essentially saying, put low Qs on everything that's unknown.
I mean, yeah, I understand, but to pursue the energy analogy, right? There's a difference between low energy and high uncertainty about the energy.
Yes,
right.
That's true. Yeah, so basically, I think the distinction that you're making is that you might have something that is low density, but you can generalize there pretty well.
Exactly.
Yeah,
exactly.
Absolutely. So I think that is a good idea, and I think that it definitely merits devising algorithms that make use of it. To my knowledge, there aren't really model-free methods that do this kind of thing, but there are plenty of model-based methods, including offline model-based methods that leverage exactly this principle, and they look at basically model uncertainty with some kind of Bayesian approach. Yeah, but I think it would be pretty interesting to devise a model-free analog of that. I'm sure such a thing is possible.
Yeah, and you don't have to go Bayesian to do this either.
Yeah, of course. All right. Let's see. Let me just find where I was. Okay, so the next question I see is from Ang Lee. Suppose I have a not so realistic but okay simulator. Do you think doing online RL on the simulator could help relieve the OOD issue in offline RL? Or in general, combining offline RL with real data and online RL with an okay simulator? I think that's a good idea. I think that you have to be kind of careful to make sure that the two processes are actually sufficiently coupled, because you might get into this situation where essentially your policy changes a lot and it's pretty happy with where it is in the simulator, but it deviated so much from the data that's not really being supported by the data. So basically a lot of the flaws in training and simulation might not be alleviated by this. If, for instance, your simulator allows for some very good behavior that is very different from the data and impossible in the real world, you might fall into that trap. So I think in general, such a recipe can be made to work, but you probably want to be careful to ensure that you still have some kind of constraint or some additional term that says, don't deviate from the data too much. So basically, maybe think of it more like data augmentation rather than proper simulation. Jan LeCun said in an interview that he thinks self-supervised learning can fundamentally solve many current ML problems, including RL, in the long term. No offense here, none taken. But how much do you think self-supervised learning might help RL? So my answer would be that I think RL is self-supervised learning. In fact, RL is maybe the most self-supervised learning. Like, self-supervised learning as it's essentially today is often kind of data augmentation supervised learning. It's supervised by data augmentation, whereas RL is supervised by reinforcement, or in the case of goal condition RL, it's actually supervised by nothing. It's supervised by dynamics, basically. So yeah, my answer, and I'd be more than happy to debate Jan on this, although I think he might actually just agree with me, is that RL is just a type of self-supervised learning. In my opinion, the good type.
Very good. So actually, Jan, he's going to be our speaker next week, and we actually have an actual half an hour conversation with Jan LeCun. So
you guys should ask him.
Yes. So Sergio, you're welcome to come back next week.
Perfect.
That'll be perfect.
Yeah. But I get the feeling that he might agree with me that it's a type of self-supervised learning. I'm not sure he'll agree with me that it's the good kind.
On the other hand, self-supervised learning is just supervised learning with a particular type of supervision.
Of course.
So it's all the same in the end.
Well, I wouldn't go so far as to say it's all the same. There's a difference in practice, but yes, there's.
No, I mean, you can think about it like how much supervision do you have, and RL you have the least, right? But in self-supervised learning, you actually have a ton of supervision, like for example, video prediction, right? Yeah. Video prediction is actually massively supervised learning.
Yeah, that's right. I think that's a good way to look at it. In a sense, the supervision that you really have in RL, like, I mean, there's reward, but that's not really the main point. The main source of information in RL is actually the dynamics. So it's a different way to pack the same kind of knowledge into the system as you would by doing video prediction.
I mean, I think, you know, to come at this from the RL end, right? What self-supervision does for you is that when the rewards are sparse, you need some other source of supervision.
Yeah.
Well, mathematically, it's all the same, but the point is that, like, you don't have enough information. You can acquire a lot of information just by observing the dynamics without even acting. But then, of course, you do need those rewards to actually decide what to do when.
So generally, that's right. I think that there's a little subtlety, though, that happens in the offline setting. So in the online setting, like, this is definitely a really big deal. In the offline setting, if you don't have any rewards, you're hosed. Like, there's nothing you can do. But if you have some rewards, the sparsity of the rewards is not actually that much of an issue. You might need to train for longer to back them all the way up, but the information is in there. And every time you back it up, you're essentially learning from the dynamics of that backup, from the transitions.
Oh,
so it's not actually, I wouldn't say that offline RL is more weakly supervised than something that learns dynamics.
I mean, totally. But in fact, in that sense, what you have now is a type of semi-supervised learning.
Yes. Right? Yeah, I think that's a great way to look at it.
Very well what the benefits of both the, think
Yes.
of it in terms of a network, the nodes that have labels and the nodes that don't have labels.
Yes.
You only need a few nodes with labels, but the ones without labels are extremely useful.
Yeah. Yeah, I think looking at it as semi-supervised learning is actually a pretty good, I guess, lens on what's going on. All right. Well, I think we're about out of time, but I can probably go through a few more of these.
Yeah, it's really up to you how much time you want to use. Plus, the longer the better. Yeah.
Yeah. Probably, I do need to go do some kid-related things at 8:30, but I can try to take a couple more. Is it possible to uncouple the auto-distribution problem in offline RL by learning a model of the environment and an expected upper bound of the reward over single transitions for each action at a state? Kind of. But you have to be careful to make sure that your model of the environment is not itself vulnerable to auto-distribution inputs. So I didn't talk about model-based offline RL at all, but the problem that happens in model-based offline RL is that you basically cook up an action that fools your model into thinking that it will transition to some really good place. So basically, your model is mostly a reasonable model, but then you give it some crazy action and thinks that it's going to go to paradise if it takes that action. So you have to somehow robustify your model. And it's kind of analogous to how you would robustify your Q functions if you're doing model-free. But if you do that, then you're good. Despite offline RL showing impressive performance on various domains like video games and robotic manipulation, do you believe that it's on track to artificial general intelligence? I mean, I don't know. That's a very big and complicated question to answer. What I do think is that, and this is where I was going with my motivation at the beginning of the talk, is that offline RL is potentially a really good choice in many, many places, because basically if we're building a machine learning system, it's because we want to make decisions. And our world is a sequential process. Our world has time fundamentally. So any machine learning system fundamentally is making decisions in a sequential process, which means that potentially any machine learning system can be framed in such a way that it's suitable for reinforcement learning. And if it's offline reinforcement learning, then the assumptions are not that different from supervised learning. They're not exactly the same, of course, because you need, sequence data and all that stuff, but it's kind of pretty close potentially to a hammer that can be used to hit many, many nails, many more nails than are being hit now. Now, as to how general that is, I'm not sure. I mean, I think in that regard, it's, that's kind of a separate question. Okay, I think probably I should head out now. It's like past 8:30. But yeah, we got through basically all the material. The only thing at the end was a bit about how there's many open problems, but I think we talked about so many open problems that the Q&A got the point across much better than my slides would have. Great.
Thank you. And it's such such a great pleasure, and so we joined your talk a lot, and thanks for so much patience for answering all the questions. And so I will. Am I allowed to share the slides with people?
Oh,
outside?
absolutely. Yeah, by all means. Yeah.
Oh, okay, great. So yeah.
Great. Well, thank you for hosting me.
Okay, great. Thank you, everyone.
Bye, everyone.